Hey, welcome back. We're at lesson number 3, permutations and combinations. This could be a long one, so just hold on tight for this one. It's actually going to be kind of fun though. This is more of the counting principle type of idea, but it's going to be giving us a much more specific count for much more difficult kind of concepts. So let's start off with permutations. A permutation is a number of ways an event can happen when order matters. Like, for example, the top winner in a race, right? First place, second place, third place, that stuff matters. So if you're thinking, how many possible ways could a race have different outcomes, that's going to be a different question versus like, how many different people could possibly win first place. Different question, right? So let's look at a kind of interesting version of this, right? How many permutations of Roy G. Biv, which is the color spectrum, in other words, the rainbow, how many different color permutations are there of it? Right now, the order that we're used to would be red, orange, yellow, green, blue, indigo, violet. But we could very easily have red, orange, yellow, blue, green, indigo, violet. Or we could have red, orange, yellow, blue, green, violet, indigo, right? There's all sorts of variations. We could start with blue, right? But if none of them repeat, how many different versions are there? So this is what we would do in this situation, right? We have 1, 2, 3, 4, 5, 6, 7 different options for that first spot. Now, if we use one of them, like let's say we use yellow first, we only have 1, 2, 3, 4, 5, 6 left to choose from, right? And so on and so forth. So we keep on losing one every time that we go and choose one. So right now, it kind of looks like factorial, right? 7 factorial. 7 factorial, so that would be 5,040 different ways that you could have that specific ordering, right? Where that one has to come first, this one has to come first. Right? So think like if you had like a very unique flag that you wanted to fly, right? Okay. Here's another example. Adriana, DeAndre, Gabriel, Ashley, Catherine, Chanelli, and Victoria all have a race. How many permutations of first, second, and third place are possible? All right, so let's see. Placement matters here, right? First place, second place, and third place. How many people are running? We've got 1, 2, 3, 4, 5, 6, 7 different people running. So there could be 7 people who win first place. Not that all 7 of them would win at the same time, but there's 7 different options of who could win. So we definitely have 7 for that first spot. But now, if they have this race and one of them randomly wins, I'm not going to pick one because I know all these people and they're in class and I don't want them to yell at me. But I know somebody's going to win that race, which means that there's only 6 people that could possibly win second place. And then, again, only 5 people that could win third place. Right? It doesn't really matter who comes in 4th, 5th, 6th, and 7th place because these are the only ones that really matter. First, second, and third. Right, so if we just multiply 7 times 6 times 5, in that particular outcome, there's only 210 possible outcomes. That's a little bit different from when we had looked at basically the same problem with 7 different choices, right? 7 different colors, but we want to know every single space changing, versus here, we only want to know the top so many. Right? If we wanted to do the top 4th places, we would be multiplying by a 4th placement here, and we would have one less to choose from. So we would get different numbers even though we're having the same number of people racing. Pretty interesting mathematics. So I'm going to show you a cool formula right here. It's called the NPR, or N permutations. Okay, the number of permutations of n elements taken r times is NPR equals n factorial over n minus r factorial. Very easy formula to use. Make sure you write it down because we're going to use it. All right, so our first example, a parade has 38 floats. How many permutations of the first 10 floats are possible? So we've got 38 permutations of 10 different, like the first 10. So what that would mean would be like, I don't know, maybe this is the first one in line, second one in line, third one in line as they walk out. So it says n factorial over n minus r factorial. That's the formula. Let's simplify this first. 38 minus 10 would be 28. So we're going to expand this. 38, 37, 36, 5, 4, 3, 2, 1, 30, 29, 28 factorial. And the reason why I'm stopping there is because I know if I expand that and expand this 28 factorial, those will both cancel out. Right, so I gotta multiply 38, 37, 36, 35, 34, 3, 32, 31, 30, 29. Oof, that's a huge number. Coming up with 1.715 times 10 to the 15th. So basically, if all of these artists that created these floats were to sit and argue about who the first 10 to walk across stage, they'd be arguing for a long time about who would be coming out first. Give me one quick second. I just want to make sure of something real fast. Yeah. All right, cool. So we got another problem right here. A tournament gives medals to the top 4 ranked teams. If 6 teams enter to win the tournament, how many different outcomes could there be for awards? So this is a little more reasonable, right? Like if you play volleyball and you go to the tournament for Division 1 states, right? There's only 16 teams that are entered to win. How many could get top 4? All right, so we're doing 16 permutations of 4. So 16 factorial over 16 minus 4 factorial. Let's simplify that a little. 16 minus 4 is 12. So if we expand 16 times 15 times 14 times 13 times 12 factorial, those will cancel. So 16, 15, 14, 13 all multiplied together would be for 43,680 different outcomes. All right, so if you watch that tournament and it turns out that Central is the first place team, and then I don't know, Shea is second place, and Mount Hope is third place, right? That's only one possible combination out of 43,680 outcomes. Pretty cool. So you're going to try this one right now. Pause the video and resume it when you're ready to check. All right. So this one says a passcode lock requires 3 letters of the alphabet non-repeating in a specific order. How many permutations are possible? All right, well, if you think about it, right, we have 26 letters times 25 letters, because we can't repeat any, times 24 letters. So 26 times 25 times 24, 15,600. I didn't use the formula for that, but if we were to have done this, right, if we said 26 permutations of 3 choices, right, that would have been 26 factorial over 26 minus 3. 26 factorial over 23 factorial would have left us with 26 times 25 times 24 times 23 factorial, and look, see, came out to be the same thing. So why am I showing you that? To show you that what we did the long way in some situations, we can deal with using permutations. So if you use that formula and you got it the same way, it just proves to you that that formula is working. So I think, yeah, we got a couple more things to look at. This is something called distinguishable permutations. These are kind of fun as well. This is like if you have something that has multiple of the same element, how many different ways can you consider something that has something that repeats? Because if that shows up in that position, doesn't it mean that it's already been used? All right, so let's say that you have so many of one particular element and another number of another repeating element. So for example, letters, right? Like the word banana. Banana has multiple A's and multiple N's, right? So depending on how many of these repeating letters you have, here's a formula that you're going to work with. Very easy. N would be the total number of overall elements in that particular word or cluster. N sub 1 would be the number of, let's say, A's in banana. N sub 2 would be the number of N's in bananas. N sub 3 would be the number of B's in banana. But then overall, how many letters are there in banana? So that's how that particular formula works. So we're going to do it with these couple of examples here. You want to write them down real quick. So this is how it works. We're going to count up the number of letters altogether. That'll be our top, our numerator. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 letters altogether in the word sleeplessness. All right, as far as S's, there's 1, 2, 3, 4, 5. Oops, so there are 5 S's. So that would be like our N would be our S's. L's. There's 1, 2 L's. So we would have 2 factorial. E. 1, 2, 3, 4 E's. So 4 factorial. There's only 1 P. We're not going to include 1 factorial because 1 factorial is just 1. And there's only 1 N, so we're also not going to include that one either. So I believe we got all the letter categories covered. So let's expand this a little bit. 13, 12, 11, 10, 9, 8, 7, 6, 5, factorial. And I knew I could stop there because this is the highest one I have. So I'm going to lift it right here and get rid of it right away. These I'm going to expand. 4, 3, 2, 1, and then 2, 1. So let's see. 4 times 3 is 12, so I can get rid of that. 2 goes in the 10 5 times, so I can reduce that. And 2 goes in the 6 3 times, so I can reduce that. So I'm going to be multiplying here. Ready? I'm going to do 13 times 11 times 5 times 9 times 8 times 7 times 3. And remember, I reduced some of those numbers along the way, and that gave me 1,081,080 different ways. So what does that mean, right? How many distinguishable ways can the letters be written in sleeplessness? What that means is I could have this S here, and I could have this L here, and these E's and the P, right? Everything in this order. Or I could possibly switch the S and the L here. I could have maybe this S be over here where this E is, right? But because there's so many of these same letters that repeat, if I put this S here, it'd be the same thing as if I put this S here. So we don't want to multiply every single thing because some of these repeat and they serve the same purpose. It still makes the S sound. So if we don't include repeats in a position, right, like if I had this E here or this one here or this one here, it doesn't matter which one of them are there. If we exclude those repeats, we get a different number than if we had just said, all right, all the possible letters here, all the other possible letters, right? It's a slightly different solution. Kind of cool. So we're going to try one more before I let you try on your own. How many distinguishable ways can the letters in Tennessee be written? All right, so first of all, Tennessee has 1, 2, 3, 4, 5, 6, 7, 8, 9 letters in it. There's only one T, so we're not going to do 1 factorial. E's, there's 1, 2, 3, 4. N's, there are 2. And S's, 2. So let's start expanding. 9, 8, 7, 6, 5, 4 factorial. And I know that those things will cancel. That's my highest one. And then I can expand these. 2 times 1, 2 times 1. Let's see. 2 goes into 6 3 times, and this 2 goes into 8 4 times. So here's what we got left to multiply. We've got 9 times 4 times 7 times 3 times 5. 3,780 distinguishable ways we can rearrange the letters in Tennessee and get different words or new words, unique words. So you've got one more here to try. Pause the video and resume it when ready to check. So how many distinguishable ways can the letters in suddenness be written? Well, let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 overall characters. There's 1, 2, 3 S's, only 1 U, so we can ignore that. 2 D's, 2 E's, and 2 N's. So we can expand this all the way down to 3 factorial. Oops, what am I doing here? Make that a 10 first. 9, 8, 7, 6, 5, 4, 3 factorial. So those will cancel. And then we've got a couple of 2 factorials. 2 times 2 is 4, so I can eliminate those. We'll do 2 goes into 10 5 times. So here's what we're going to multiply. 5 times 9 times 8 times 7 times 6 times 5 again. Right? 5, 9, 8, 7, 6, 5. Total 75,600. All right, that's it for permutations. However, I did tell you that this was going to be kind of a long one because we've only gone over permutations. This might end up being 2 different lessons as far as notes go in class. I'm not 100% sure, so you could pause the video here if you wanted to and pick up from here when you're ready for combinations. But we're about to look at combinations next. Alright, so combinations, it's kind of like a combination plate, right? It doesn't really matter what order they put the food into the little box for you. You just want the food and you want to get out of there, right? So we're going to use that kind of mentality with this. Order doesn't matter. I don't care how you put it in the box, just put it in the box, right? So when order doesn't matter, like playing a card game, right? If you have a deck of cards, it doesn't matter what order those cards come out because you can rearrange them in your hands, right? Or maybe if you're sitting around a table, it doesn't matter where you sit, you're all seated. Okay, we can use combinations. And we use this one formula, which is called N choose R, not combinations of R. I know it sounds weird, but we call that N choose R. And here's the formula. Looks very similar, right? N factorial over N minus R factorial, but the difference here is that we have R factorial included on the bottom. Now there is a proof to this that I'm not going to go over right now in this class because it's Algebra 2, but if you're super interested into it, we could get into that in pre-calculus, or even other courses could possibly show you that proof as well. So let's start using this combination, this idea of order not mattering. Okay, so I'm going to leave the formula up for us to see. So you go to the salad, nope, scratch that. You go to the nacho bar, has 18 toppings to choose from, and you can pick up to 6 different toppings. Right, so it doesn't matter what toppings you throw onto your nachos because it's going to taste delicious, right? So it doesn't matter the order, it just matters that you're choosing 6 different toppings out of 18. So how many unique combinations of not salad, but nachos can you make? So again, order doesn't matter here. We can throw on whatever first, whatever second, it really doesn't matter. But we have 18 and we're choosing 6. So we're going to do 18 factorial over 18 minus 6 factorial and 6 factorial. Let's reduce this a little bit more. 18 minus 6 is 12. So now we can start expanding. 18, 17, 16, 15, 14, 13, 12 factorial. Again, I know I can stop when it matches my highest one on the bottom, but I am going to expand the 6. That's going to help me choose to get rid of some stuff here, right? 6 times 3 is 18, so I can get rid of that. 5 goes into 15 3 times. 4 goes into 16 4 times. 2 goes into 4 2 times. So there we go. We cleared that up a little bit. So here's what we got left. We got 17 times 2 times 3 times 14 times 13. That would be 18,564. So if there are 18 different toppings to put onto your nachos, and you can pick up to 6 different toppings, that's the number that you could, or different combinations you could throw onto that. All right, so you're going to try this one out. Pause the video and resume when you're ready to check. All right, so let's see what's going on here. You're playing a video game, right? And 4 different people can play at the same time, like Smash Brothers, for example. But right now you haven't unlocked all the characters. There's only 14 characters to choose from. How many different combinations could you play? It really doesn't matter, right? First player, second player, third player, all that doesn't really matter because no one's won the battle yet, right? So in terms of permutation or combination, order does not matter here. So we have 14 and we're choosing 4 because there's only 4 players playing. So 14 factorial over 14 minus 4 factorial times 4 factorial. To reduce a little bit more, 14 minus 4 is 10. Now we can start to expand. 14, 13, 12, 11, 10 factorial. That's where I'm stopping. I'm going to expand 4 though. I can get rid of my 10 factorials. 4 times 3 is 12. 2 goes into 14 7 times. So let's see. We got 7 times 13 times 11. That's 1,001 different ways that you could play a video game with 4 people and you each choose out of 14 characters. That would keep you entertained for quite a while. Hey, great news, that's the end of that lesson. So we've covered both combinations and permutations. If anything is learned here that's most valuable is the difference between a permutation and a combination. Permutation, order matters, like a race. Combination, order doesn't really matter. It's like sitting around the table. You can have all sorts of different arrangements, but ultimately people are just sitting down. So once we get to the next lesson, probability, that distinguish about order mattering, that'll come into effect when we talk about different types of probability, which is what we're getting into next. So I'll see you at that next video. Bye.